Okay, we are going to solve some recitation problems. They will be about last week's course, which is about series, alternating series, and some convergence tests that we are going to, observe, analyze, and talk about. Let's start. It is my first question. In this video, I'm gonna solve all these questions. Let's start. A. Okay, it says that the sum from 1 to infinity of ln 1 plus 1 over n squared. So you always try to n term test whether this general term is going to be zero or not, because if it is not zero, then this series is divergent anyway. Anyway, here it is when you take the limit n goes to infinity, this will be 0 and this will be ln1, which is 0. So we don't get any negative result from n term test. So what can we do? We can do a limit comparison test or comparison test. We have bunch of methods. Okay, observe ln x is always less than x if x is positive. Okay. You can also prove that exercise derivative. Now, using this idea, we can say that this ln is, by the way, which is positive. Now, 0, which I mean that everything is positive. So we most of the time only use this convergence test for positive series. I mean, the general term is positive. Anyway, ln plus n square is then less than n square, and this series 1 over n square is convergent by p-test. So by direct comparison test, the original series is also convergent. Okay. Now you can also use another method. This is method 1. Method 2, limit comparison test. So try to take the limit because ln1 plus x is behaving x at infinity. So that's why I am applying limit comparison test to 1 plus 1 over 1 over n squared. Yeah. So ln 1 plus 1 over n squared and 1 over n squared. So it is like when n goes to infinity, this is 0, this is 0, so 0 over 0. So I can apply L'Hopital rule, but in this discrete case, I cannot. So go to continuous variables. Because in this case, you are taking limit on natural numbers. Okay. So on continuous variable, we have limit x goes to infinity. The same thing. I'm gonna just repeat myself. And let me make some space. So 0 over 0, we have just observed that. Apply L'Hopital rule. L'Hopital. So it is limit x goes to infinity. Take the derivative of the numerator. We have uh, minus 2 over x cubed over the inside. This is inside derivative. And in the denominator, we have the same thing, this derivative. So minus 2 over x cubed. So they will just cancel each other. So we have limit goes to infinity. So this is just 1, right? When x goes to infinity, this is 0. So 1 over 1 plus 0 is 1. So it means that it is less than infinity and bigger than 0. So it is by limit conversion test, they behave the same, right? Let me just copy and paste this limit comparison test. Okay. We have two positive sequences. If you find the limit L is neither infinity or negative, then we can say that they both behave the same. Okay. That means that, let me finish. Then by, then, and also, and by p-test, this, by the way, yeah, we have more details. Then this limit is, limit, in the discrete case is also 1. So, and by p-test, right? Because 2 is bigger than 1. And by limit comparison test, the original is convergent. By the way, since it is already positive, it is absolutely convergent. Okay. We talk about absolute and conditional when there is some minus or plus. I mean, the signs are changing. Then we talk about absolute and conditional convergent. But here, since this is already a positive series, it's absolutely convergent or just convergent. So let me go to next question. Ah, yok bu değil. Okay, now this is B. Allah Allah. Okay, let me copy and paste. Let me solve B. So take the limit of the general term immediately. That's your first thing dealing with series. So limit n goes to infinity arc tangent 1 plus 1 n squared. But you can see that this is a continuous function. So you can interchange with uh, this function on the limit because I know that limit exists, right? It is 1, which is not equal to 0. So divergent by n-term test. Let's do C. In this kind of confusing general terms, you might try to take the, I don't know, limit of the general term first, but it is, very hard to calculate. Uh, just 1 minute ago, I said that always check the limit of the general term. I mean, if if the general term is simple enough. In this kind of things, you can apply root and ratio test. Since we cannot take the root of everything, so it is better to use ratio test. Let's try ratio test. Uh, Let me copy and paste the statement of the ratio test. So this is the statement. Let's say that an is always positive after some point. In our case, it is, right? Everything is positive. And calculate this limit. Let's calculate. An plus 1 over an. It means limit n goes to infinity. Um, n plus 1 factorial 3n plus 1 over 2n plus 1. Don't forget to write plus 1 inside n. This is not 2n plus 1. This is 2n plus 2. Again, you make some mistakes. You might. Factorial 3n 2n factorial. Let me simplify. N goes to infinity. So I have 3 n plus 1 and 2n plus 2 2n plus 1, right? These are gone. These give me this thing. These are give me this thing. Okay. If I calculate this, you will see that this is degree 1 polynomial. Everything is positive. This is degree 2, so this limit is 0. So ratio test only talk about this 1, right? Or 0. So since it is equal to 0, so it is 0. So it's convergence. So the series is convergent by ratio test. So let's solve part D. Let me rewrite it. ln n cube. It is rather easy. We have talked about this ln n is less than n. We have already talked about this. Use since we are only dealing with natural numbers and this is already bigger than 2, so we don't have to mention, but this is happening because of this. Whenever this is okay, so we are going to use direct comparison n over n cube. So this is 1 over n square. And observe that 1 over n square is convergent by p-test. And then this is convergent by direct comparison. Comparison test. Because everything is positive again. What about part D, E? This thing. Again, let me copy and paste. This is not very good. Let me separately copy and paste because it is not efficient. Let me try in this way. So you can apply end-term test, etc. But since there is a very big power, why don't you use ratio test? So consider limit n goes to infinity nth root of the general term. Okay. So everything is possible. So this no need for this absolute values. So it's like limit n goes to infinity. So these n's are gone. So we have 1 over 2 plus 2 over n. So this is going to be 0. This limit is 1 over 2. So, and this is less than 1. By the way, the conditions of the ratio and not, yeah, about these inequalities are the same, ratio and root test. So let me again just copy and paste to show you this is the case. Huh. This is again positive. You take the nth root of the general term. If your this limit is strict less than 1 and equals to 0 or between them, this is convergent. Okay? In this case, it is. So it is convergent by root test. Let me go to new question. So again, look at this. These are bounded things, right? You can ask that. Before that, everything was positive, but here this sign can be also negative or minus. Yes, you are correct. So that's why we are going to look at in mm, absolute value case. These are okay, sometimes negative, sometimes positive, but they are bounded from below and above. So uh, observe, recall, whatever recall. So let me put everything inside some big absolute value. So above is less than 2. So since this denominator has extra term, it is less than 2 over n square, right? And this series is convergent by p-test. And this original thing, the series is convergent, absolutely convergent. Now, because we take the absolute value, absolutely convergent by comparison test, direct comparison. By the way, recall that since it is absolutely convergent, it is convergent, right? Recall, remark ya da absolutely convergence, absolutely convergence implies uh, convergence, but not vice versa. Okay, and these are the exact examples of conditional convergence series. Let me take two at a time. Maybe one is too few. Huh. Let me solve G. So you can rewrite this series. Let me call it S. We can rewrite this series as sine square or over e to power n. Now observe that this general term, again, this numerator is less than something. This is bounded, right? Since sinus is always bounded by 1, so this is also bounded by 1. So when you take the square, it is still bounded by 1. And 1 over e to power n is a geometric series, so it will be convergent. So let me do it, what I verbally explained already. Sine en square over en. By the way, everything is positive, right? Because we are taking square and e to power n is always positive number, less than 1 over e to the power n, and 1 over e to the power n or 1 over e to the power n is convergent, because since it is a geometric series with 1 over e is less than 1. Okay. And by direct comparison, the series S is convergent. So let me do H. This is a telescopic series, right? When you call this thing AN, so this is AN plus 1. So let me call this whole series as H, bigger H, big H. So big H is just limit big N goes to infinity, sum big N, little n from 1, AN minus AN plus 1. So it's like limit big N goes to infinity, A1 minus A2 plus A3, blah, blah, blah. At the end, it is A bigger N minus A bigger N plus 1. So as you can see, there are, by the way, this should be 2 also. Huh. They are cancel each other. So what do we have is A1 and A bigger than plus 1. When you take the limit, it is just A1 minus limit and goes to infinity A n plus 1. So this is just sine 1 over 2. And this is, let me calculate it. I don't know what it is. Uh, calculate limit n goes to infinity a n plus 1, which is limits. Right, let me check it again. Yes, correct. This is n plus 1. Okay, whatever. So let me put n plus 1. Oy, what is this? Okay, what is the limit of insight? It is 1, right? And sin is continuous, so we can interchange. It is like sin is 1, which is also convergent. So this thing is equal to, actually, let me write this. Sinus 1 over 2 minus sinus 1. So convergence. The series, I mean. Because this calculation belongs to the series, right? We call big H to our original series here. Yeah. Do you have any question? Oh, I thought that it is real recitation. I mean, it is real, but not on live. Aynısı mı? Oh, sorry. Okay. How do we deal with this thing? Since there is n, we can apply ratio test immediately. Consider limit n goes to infinity. Take the ratio. And so we have limit n goes to infinity. Maybe you can put absolute value, right? But arctangent n is bounded by pi over 2, so this is always positive, so no need. Pi over 2 minus arctangent and when you take the limit, this is gonna be pi over 2, so this limit is 0. So if it is 0, it means that it is strictly less than 1, so it means that the series convergent, right? Let me remind you the conditions of ratio test, root test. If this limit is 0, then it's convergent. So we are in the good spot. So convergent by root test. Let me solve these things. J. Okay. Um, it is a bit weird, right? When you take the limit, this will be 1, this is 1 minus 1. So there's no conclusion of because of n-term test. But there is something, okay, observe that. Observe limit x goes to 0, 1 minus cosine x over x square. Yes. So when you take, okay, can you calculate it? Maybe you can not, right? Because it is just 0 over 0. But apply L'Hopital. So you get limit x goes to 0 sine x over 2x. So this limit is just 1 over 2, right? Okay. Now I know. Uh, so this is an observation. Okay. If you can recall this, you can observe. And instead of x, if you put 1 over n square, now it implies limit n goes to infinity, 1 minus cosine 1 over n square, 1 over n to the power 4 is 1 over 2. Okay. Because the limit is the same, I just change the variables. But using this trick, I get some comparison, limit comparison, right? Because I'm now comparing this thing with 1 over n to the power 4, and I get something less than one, something less than infinity. So it means that this thing will behave like 1 over n to the power 4, which is convergent. And convergent by p-test. And by limit comparison test, so it's less than infinity. So it is less bigger than 0. By limit comparison test, this series convergent. Okay, because of this limit. Now let's do L. Okay, so now it is alternating, and if you take the absolute value of this thing, it doesn't converge because we get n in the denominator, and there is also still ln cube n in the numerator, which is an increasing function which prevents convergence. Okay, so it is not will be convergent. You can check, but this is not the original question. Original question asks about some, oscillation by this minus one to the power n. So what should we do? Maybe we can apply uh, alternating series test. Let me copy and paste. What is this series? This is alternating series test. It says that suppose that you have, in our case, let me rewrite. Neydi? Huh. In our case, RAN is the whole, but let's separate BN, which is just the positive series, positive part. And we are going to observe that this positive part will be uh, decreasing. So this part 2 says that. And the limit will be 0. If they are satisfied, then I can say that this whole series is convergent. Okay, let us try. Let me just first. Okay. Ah. Absolute value of minus 1 to the power n ln cube n over n is just ln cube n over n. Because everything else is positive. So let me call it bn. Oh, okay. So let's check. By the way, alternating part is okay in our case. Now, let's say bn is less than, no, bigger or equal to bn plus 1. Okay. So one way to show it, yeah, or decreasing, decreasing. One way to show it is, go to continuous parameters, yeah, x variables, and take the derivative. Okay. Consider, take the derivative 3 ln 2x 1 over x minus ln cube over. I'm applying quotient rule. Now let us simplify. 3 minus ln x over x squared. As you can see, this thing is always bigger than 0. It is actually never 0, but it's strictly positive because we don't care about this 0 because this original series is from 40. Okay, if you recall the problem. But here, 3 minus x is, okay, negative. 3 minus ln x is negative for x is bigger than e to power 3 desek. Okay. I can directly write it, but let us analyze. This can be written as ln e to the power 3 minus ln x. Okay. Now, if x is bigger than e to the power 3, okay, now we are fine. Okay. If Okay. Now if x is bigger than e to power 3, which is bigger than 27 or something like that. Okay. I'm considering e is like 3, then it is 23, etc. Anyway, so I mean, eventually it is decreasing. Okay. Eventually, f prime x is always strictly less than 0 for x is bigger than e to power 3. So it is finished, right? Since continuous part is decreasing, this discrete part is also decreasing. So this is shown. Let's show the limit. N goes to infinity. And in our case, ln cube n over atıyor muyum? And no, it's correct. How to show it? So let's go to, yeah, it's like obviously L'Hopital rule, but we cannot apply here. So again, we go to continuous part. So now go to x variables, continuous or real. Anyway, limit x goes to infinity, ln cube x over x. So it's like infinity over infinity. Take the L'Hopital rule. Okay. Limit x goes to infinity. 3 ln square x 1 over x over 1. So again, it is 0 over. So this x can be go to denominator. So let me rewrite it. Again, infinity over infinity. Le hop limit infinity ln x. So this 3 is actually 6. This is 1. So again, yeah, last time. So I need to solve it precisely because it's a recitation video. Hope limit x goes to infinity 6, 1 over x over 1. It is 0. So every L'Hopital is equality now because limit exists. So this limit is 0, then we have shown that. So series minus 1 to the power n ln cube n over n is convergent by alternating series test. By alternating series test or by ACT, AST. I mean. And then, okay, this is finished. We have some questions. Uh, Let us calculate an okay. This series can be written as n equals from 0, 1 over n to the power n plus 1 over n, right? Because this is n to the power 1 over n. Yeah. Okay, now you can. So there is no n, but there is a mistake that I made. This should be 1. Now, if I get rid of this 1 by using limit comparison, so it's like hinting that, okay? Now observe, try limit n goes to infinity. 1 over n, 1 plus 1 over n, 1 over n. So limit n goes to infinity, 1 over n, 1 over n. So it's like a very basic limit question. Okay, so it can be written as limit n goes to infinity e to the power minus 1 over n ln n. Okay, now calculate. Let me calculate in the real case. I mean continuous. Yeah, continuous means that my values in the number system are not discrete. They are very close to each other. It means that I can take the derivative. That's the whole reason. Now, ln x over x. So it's like infinity over infinity. You should probably know this limit. It will be 0. Anyway, let me calculate anyways. 1 over x over 1, which is 0. It means that, so this so this limit is equal to e to the power minus 0, right? Is e to the power x is continuous because we can change this limit above, and we know this result of this limit, which is 0, so it is e to the power minus 0, which is 1, right? So it means that we can say that and is divergent by p-test, and by limit comparison test, this series is divergent, right? Because we have found that this limit, all right, this limit of comparison is 1, not 0, not infinity. So they behave the same. Of course, there are something going around when the limit is infinite or 0, but we don't have to deal with it. If they are between 0 and infinity, so their behavior are the same. So it is finished. Oh, let me solve this question. Okay. Okay. I think we should apply ratio test. Observe, because we cannot take the roots. We don't have any idea about this limit comparison. There's also no direct comparison way to me. Maybe you can find a way. Okay. But here, ratio test is very good. Limit. Let me call this an. An plus 1 over n goes to infinity. So this is equal limit n goes to infinity. 1, 200, and 2025, 3 n plus 1, 3n over n 2025. So this limit is actually, let us simplify, 1 over 3 n 1 plus 1 over n to the power 225. So this will be 1 because this will be 0 when n goes to infinity. And 1 to the power 200, 2025 is again 1. So this limit is 1 over 3. So it is strictly less than 1. And by ratio test, so by ratio test, the series is convergent. Okay. Ne kaldı? Ah, this kind of things. Let's do M. Observe that the absolute version of this series is divergent. Is divergent since 1 over 3n is divergent by p-test, and the limit n goes to infinity 1 over 3n 1 over 3n plus 1 is just 1 by limit comparison test. Okay, so absolute, so it is not absolute value. So the series is not absolutely convergent. But there might be some hope still. So let's analyze. So let's call define Bn to be absolute value of the general term, which is just 1 over 3n plus 1. So observe very obviously limit n goes to infinity 1, 3n plus 1 is 0 and 1 over 3n plus 1 is decreasing. Either using either using derivative or it is then 1 over increasing sequence, so it is decreasing. And uh, by then not n by alternating series test, the series is convergent. Okay, so this positive absolute value part of the general term is decreasing. Limit zero, then by alternating series test, this is convergence. Okay, but absolutely it is not convergent, so it is conditionally convergent. It is called conditionally convergent. Okay, let me do P, which is the last one. Sinus ln n over n square minus 1. Okay. Mm-hmm. Okay. Denominator is bounded. I mean, numerator. And okay. So we are fine. So I'm gonna show that this thing is absolutely convergent. 1 over n square minus 1. Okay. And limit goes to infinity. 1 over n square, 1 over n square minus 1 is 1 and 1 n square is convergent by p-test. Okay, I have I have said a lot of things. This is comparing this series with this. And this thing is comparing this thing with 1 over n squared. And 1 over n squared is convergent. And this limit is 1. So everything will be convergent. Okay. Okay. So it's convergent and convergent by limit comparison test. And this is convergent ln n over n square minus 1 is convergent by this is absolute convergent by the absolute convergent by direct comparison test because of this inequality. Okay, so it's the end of this kind of the convergence test. I think I'm gonna do several more questions about estimations and some. Okay, let's finish. Let's also solve estimations here. Then we can finish our recitation. So it's already a very long video. I am exhausted. So But we have deal with almost every test of convergency. And since we won't have power series and okay, let me also check it. Zafer Hoca sent you the mail, right? About this context. So let me check it again. So where are you, Zafer Hoca? Yes, power series and Taylor series will not be covered and will not be in the this semester. So I am gonna just finish with estimations. Let me also check my notes. Yes, some tests, alternating series test. Okay. So let me give you the thing that I'm gonna use or do. Ah, I have already prepared. Okay. So first of all, let us remember this estimation theorem. Okay. But we are only dealing with alternating series. Or alternating series. Alter series. Okay. Yazıyorum sana. Okay, sorry. If the sequence satisfies the condition of the alternating series, I mean this. Okay, let me also copy and paste. Why not? So the series will be convergent. So we will check that series will be convergent by this alternating series test. Okay. First, check this alternating series test. So first the series will be alternating, then post part will be decreasing and limit will be zero. Then we can estimate if you like to estimate. Okay. So there is also an example. Let us try to apply this alternating series estimation example. Yes. So we will find this error. Okay. Okay. How many terms of the series are needed to compute the sum of the series with error less than? Okay. So this is my error, right? This is my error. Error. Right? Because S means in this case the whole calculation from M1. And this Sn means partial sums. I don't know. Let me go K, K1, A, K. Okay, this is the full series. This is the partial sum. So we are going to calculate which index partial sum is satisfying this error. Okay, so error, or okay, S minus Sn. Let me use the Zaferojas notation. He always uses this big N. Or in our case, it is like infinity and from one. Let me call it an minus bigger than an. This will be less than the consecutive one, or this is like a n plus one. Okay, so not equal, less than. If I can find a bound for my term, okay, if I can find a bound for my term, then I can find that this error, this whole will be less than this thing, and I will find that this finite sum will be enough, okay, to calculate the whole series with this error. Okay, so aim is to find possibly minimal number of n such that this an plus 1 is less than error. In our case, 1 over 1000 or minus 3. Yeah. So what is my original series? So an is this. What about this an plus 1? Let me calculate. So it is 1 over 1 plus 2 to power n, bigger n. Okay. So my inequality is 1 over 1000. So let me solve it. So solve it. Okay. I have, I need to have 1, 10 to the power 3 minus 1 should be less than 2 to the power n. So it's like 999. Okay. So make a table. You can directly say that if you choose n to be, I don't know, 100, it will be satisfied. But we are looking for minimal, such minimal number n. So that's why we need to check at each step. Okay. So make a table. Let me call I. This is n. This will be 2 to the power n. Okay. At each n, I'm gonna check this 2 to the power n is bigger than 999 or not. For several n's, it is obvious, but I'm not sure about. Okay. What about 5, 32, 6, 40, say, 64, etc. 129, 8, 256, 9, 5. Maybe you can start from 9, but I'm very bad at this kind of things. That's why I'm starting from very beginning. So at 10, it is like 1024. So this is the minimal number that's satisfying this thing, right? By the way, there should be some mistake because this should be n plus 1, right? So this should be n plus 1. So if n is this, so n plus 1 should be 10, so n is 9. Is minimal, so n must be 9. So it means that infinity n from 1 minus 9 n from 1 or, by the way, question is finished, but I'm over explaining. N from 10 to infinity is less than 10 to the power minus 3. Okay. So using just 9 numbers, you can estimate this whole series, infinitely many, yeah, consisting of summation of infinitely many numbers, can be calculated by 9 numbers. Of course, we then given a error. Okay, that's the power of estimation. So let me maybe do one more example, then we can finish. Okay. Um, Let me find a hard one. I don't know. Um, maybe this thing. Again, we are going to estimate. Let me create some question. Estimate with error less than uh, point 0, I don't know, 25. Bu da çok az oldu. 0, 2. So first, let us understand this series S is an alternating series because we can apply this alternating series estimation for only alternating series. So, observe that this can be written as minus 1 to the power n. So this whole series is minus 1 to the power n dot n over 2 to the power n. Okay. So this is my alternating part. This is always positive part. So Bn, let me define minus 1 to the power n to n will be n over 2 to the power n. Okay. So let's check. Limit n goes to infinity, n over 2 to the power n is 0 or not. So it will be 0. Check exercise. Also, n over 2 to the power n is decreasing. Again, check exercise. Now, by alternating series test, this series S is convergent. So it is the first thing in the alternating series estimation. Now, let us estimate. So what is my error? Error is just infinity n1 an. Let me call whole an minus bigger n1 an is just uh, an plus 1, right? In this case, it is n plus 1 over 2 to the power n plus 1. Okay, I want, by the way, this is not equal, this is less than. Okay, this thing. I want this to be less than or equal to 1 over, not 1, 2 over 100. So let's solve this. Solve it. Let me make some space. Okay. Now it is like 100n plus 100 would be less or equal to 2 to the power n plus 2. Okay, I want to make this happen, okay? I want to make 2n plus 2 minus 100n bigger or equal to 100. So let's make some table. So it will be n, and it will be 2n plus 2 minus 100n. When n is very small, 1, 2, 3, 4, 5, this will be bigger. Okay, let's try very big numbers. For example, try 10. When it is 10, I don't know. Okay, 8. Maybe 8 is nice. When n is 8, so it's like 2 to the power 10, but I don't recall 2 to the power 10. So it is 124, 124, 124 minus 800, right? It is n 800. So it is good, but it is maybe, yeah, it is bigger than 100, but maybe let's try 7 then. So it's like 5 uh, minus 700. It is not, it is even negative. Okay, now my estimation was correct then, very good. 8 is the smallest number. So 8 is the minimal natural number satisfies this inequality. So error, this whole series, so this whole series an is from n equals to 1 course to 8 is enough. Okay, estimates the original series with error less than um, 0.02. Okay, as desired. So now it is 8. Okay. Okay, it is finished. So these are all your 14th week's recitation. If you encounter with some problem or if you see something is not right, please make a comment, email me before the exam. Let me remind you the exam. It is, let me check from both the class. It should be 8th December. Schedule. Uh, Tentative syllabus. Yes, it is January, not December. January. So it is 8th January at 9:30. Exam places and the other things about the exam will be emailed soon. Okay. See you. Have a nice weekend and best. Bye bye.